Hey everybody, it's Ripley back again. We're talking about exponential growth and decay. Now, I don't remember how, or I don't know how many of you remember this from, I think it was Algebra 2. You may have seen it again in pre-calculus. But remember this formula. It was y of t equals y naught e to the kt, right? And we already established back when we first started putzing around with differential equations that the solution, that this is a solution to dy over dt equals ky. Remember how we did that? We took the derivative and then we just sort of algebraically jammed this in. But what I want to do is I want to actually prove that using separation of variables. Okay, so here's what we're going to do. We've got this, let's ignore this for a sec, but we're going to reprove this using separation of variables. This is our differential equation right here. I know that y naught equals y of 0. In other words, this is the quantity of something when at the initial time. Now, let's back up for just a sec. Think about this. Think about what this differential equation really says. It says the instantaneous rate of change of an object, of a quantity, is proportional to the amount of the quantity that is there. The example that I like to give that I think really illustrates this best is, you know, out in the Midwest they don't have reservoirs where they can put their water like we have at Boca and Stampede and Prosser, right? They don't have these open air reservoirs, so they put them up in these towers. If you were to fill one of those towers with water and then go underneath it with a broom handle or something with a sharp end on it and punch a hole in it. So you got one of these, they're sort of spherical towers, right? And they sit up here. If I fill this thing up with water and then I punch a hole in the bottom of it, in addition to going to federal prison, which would be a bummer, what would happen? Well, initially you've got all the weight of the water pushing down, right? So you'd have this gush of water out the bottom, right? But as the water, there became less and less and less water, the rate that the water was leaving the sphere or leaving the reservoir would decrease, correct? Which implies that the rate of change, which in this case happens to be the rate at which the water is flowing out of the tank, is proportional to the amount there. That's a really common understanding of this differential equation. However, once I can link this differential equation with this solution, which I realize we already have done algebraically, now I'm going to use calculus to do it, we got a whole range: exponential growth and decay, standard issue, pre-calculus / algebra 2 mathematics, nothing hard. This section, by the way, this section and the following section are probably two of the easiest sections, excuse me, that we have. Okay, you ready? Here we go. So I know that my initial amount, y naught, is going to be y of 0, right? It's just however much you have. So in this case, that would be how much water was in here at the initial time. Another instance would be, we've all done the bacteria problem, right? It's the initial amount of bacteria when we started our stopwatch, right? There could be 1, there could be 1,000, there could be however many we want it to be. All right, so that's it. Now, here we go. I know that dy over dt is equal to ky, and I'm going to separate my variables. So I'm going to bring dy over y. I'm going to leave my constant. Remember, leave your constant with your independent variable. But Ripley, there is no independent variable. Yeah, but there's about to be. Okay, so dy over y equals k dt. Take an integral. I know that the natural log of the absolute value of y is equal to kt plus c, which if I take e to the, right? If I take e to the, then I know that I end up with y equals a e. Whoops. Let's slow it down there, mister. I apologize. I end up with e to the kt times e to the c. Remember that? Which is just a e to the kt, which is what y of t equals. Well, this and this are not the same. However, do you agree because of this piece of information right here, I can say y of 0 is equal to a times e to the k times 0, which we know by definition is equal to y naught. Well, e to the 0 is 1. This implies that a equals y naught, which implies that y of t is equal to y naught e to the kt. Isn't that cool? That's awesome. And now, really, there is no calculus in 7.4. It's all Algebra 2 stuff that you've seen before, but it's also getting you acquainted with some of the language of how these things work. You guys remember Newton's, excuse me, do you remember Newton's law of cooling? Newton's law of cooling, I'm going to write it down, and you may say, wait a sec, why are we talking about this? Newton's law of cooling, and this came out of Algebra 2 as well. Some of you have probably seen it in your chemistry and perhaps your physics classes as well. And what it says is that temperature, now this is going to get crazy because I'm going to have capital T's and little t's, but just bear with me. Capital T is temperature. So T as a function of time. So think about this. It's the standard issue, right? You pull a pizza out of the oven, you set it on the counter, right? And this thing cools at a rate of, not at a rate. We know that the formula for the temperature of the time of the pizza at any time t, little t, is the temperature of the surrounding plus the temperature of the surrounding, the initial temperature minus the temperature of the surrounding. We need that thing to be negative, don't we? E to the kt. And you probably remember, hopefully, that this k has to be less than 0, because as t gets huge, I want this term to go to 0. Right? Let's explore that for a second. Think about that. As t gets big, e, if this guy's negative, e to the negative gets huge, right? Or this term, kt, gets huge in the negative direction. E to the huge negative is really close to 0. This all goes away, and guess what? Your pizza cools to the temperature of the surrounding. Well, Newton came up with this rule. He didn't really come up with this rule. He didn't even have to. What Newton said is he said that the instantaneous rate of change of the temperature as a function of time, I apologize for the big T, little t, but there's not a whole lot of other ways that we can do, is proportional, that just means that there's my K, to the difference between the temperature at any time t and the surrounding temperature. If you think about that, it kind of makes sense, doesn't it? The difference between the pizza and its surrounding is going to have an effect on how quickly its temperature changes. It's kind of like this analogy, right? I mean, the larger the difference, the faster it's going to cool at the time that it's really, really hot. But as it gets closer and closer to the temperature of the surrounding, it begins to cool less and less quickly. All right? It loses temperature less quickly. All right? Well, watch. I'm going to show that this guy right here is a solution to this differential equation. It's easy. You use separation of variables. Watch what happens. I get d capital T over capital T minus t sub s. Now, careful. This guy right here, we've got to remember, constant. This is not variable. All right? There are lots of t's floating around. We've got to be really careful about what we do with them, okay? Equals k dt. Take the integral. This implies, hopefully we've done this 1,000 times, that we know that this becomes the natural log of the absolute value of t minus t sub s, which is equal to kt plus c. Easy so far? Nothing to it? All right, remember, we're trying to solve by the time we're done. We want t as a function of t, so I'm going to solve for that t right there, that capital T. This is a constant, this is a constant, this is my independent variable. I'm going to e to the, and I get t minus t sub s is equal to e to the kt times e to the c, so this is equal to a e to the kt. Nothing to it, right? So t, this implies that t as a function of t, now I'm going to start writing this out so we don't get too confused. Again, lots of stuff going on. T as a function of t is equal to the temperature of the surrounding plus a e to the kt. Well, now wait. Don't we also know a certain amount of information? We know that the temperature of the thing, which I'm just going to call T naught, is equal to T of 0. That's the temperature of the pizza when I pulled it out of the oven. All right, if you think about it, it could be the temperature of the soda when I pull it out of the fridge. In other words, we could apply Newton's law of cooling to Newton's law of heating too, right? Think about that. It's got to work the same way. Okay? So here we go. Doesn't this imply that T of 0 is equal to T sub s plus a e to the k times 0, which we know equals T naught. It's just the initial temperature, very much like this was the initial quantity that we were talking about. I know that e to the k times 0 is e to the 0, which is 1, which implies that T sub s plus a is equal to T naught which implies that A equals T naught minus T sub S, right? And this is equal. This implies that T of T is equal to temperature of the surrounding plus the initial temperature minus the temperature surrounding times E to the KT. Well, by the way, we should probably do that, right? Right? And that's this guy right here. This guy right here. Whoops. Whoops, missed a little bit, didn't I? This guy right here is the formula that we learned back in pre-calculus, and now we have it, and we proved it using separation of variables and solving for solutions. I think that stuff's just awesome. I love it. I think it's cool. Okay, that's it. Believe it or not, got a couple formulas. Truthfully, the calculus basically proves the section, and then in the section, you're just going to use the fact that we know that we have these exponential growth and decay equations, and you're going to play with them. All right, enjoy. Hope you enjoyed a nice short lesson. I know they've been kind of beefy lately, so enjoy this short one, and I'll see you in class. Have a good